Hello, and I would like to welcome you to today's webinar, which is a joint presentation between Aerospace Testing International and Tpac. My name's Ben Sampson. I'm the editor of Aerospace Testing International magazine, and today's webinar is titled Advanced Ultrasound Instrumentation for Aerospace. So as the title suggests, today's the presentation is all about ultrasound. Tpac, the phased array company, a specialist in this. We are lucky to have with us today Fernando Ojeda, who is the Director of Business Development from Tpac. Hello, Fernando. How are you doing?
Hello, Ben. Yeah,
Great.
good.
Yeah, good to have you with us. Thanks for your time. So Fernando has some 22 years in NDT. Is that right, Fernando?
Yeah, that's right.
Yeah. Okay. Wonderful. And you work a lot in aerospace with aerospace clients?
Yeah, aerospace has been my activity, yeah, for the very beginning and especially in the last 10 years.
Okay, right. Yeah. So we can look forward to some really good detail on this technology then with you. So just a couple of housekeeping things. We'll have a short Q&A session at the end. If you have a question during the presentation for Fernando, then please do enter it on the box that you should be able to see on the right hand side of your screen. We'll come to that afterwards, but we are quite restricted for time. So if we don't come to your question in the session, Fernando does get a record, or you can email him or me, and we'll get back to you after the presentation. I think that's about it, Fernando. So I'm really looking forward to seeing this presentation. Please do start when you're ready.
Okay, thank you, Ben. First of all, I would like to dedicate a few words on who we are. We are a team of about 60 people based in different countries in North America, Europe, and Asia. We design and manufacture ultrasound instruments and solutions. Our profile is strongly focused to engineering and ultrasound physics. And our organization is quite focused on technology and support to customers, mainly integrators. We operate under two brands, which are called Advanced OEM Solutions, or AOS, and Tpac, the phased array company. In AOS, we provide the core technology for the ultrasonic instruments that our customers integrate this technology in different solutions like scanners, crawlers, or robots. Based on these technologies from Tpac, we provide terminated rack instrumentation, also the engineering and software. And we also collaborate with different integrators, system integrators, so we can provide, in collaboration with them, different automatic and robotic solutions to the aerospace market. Aerospace applications. Well, I would say that we are quite transversal in terms of applications in aerospace. We are working for the production and maintenance of different structures in engines and aerostructures. We have specific solutions for the inspection of metals and composites. Specifically, we have some solutions for inspecting high attenuating materials, including dry inspection. And we normally, many times start with NDT problems that appears or are originated by the new materials and new processes like additive manufacturing. And we also have specific solutions for the inspection of complex shapes. Robotic applications are a very common one for us. As I said before, we are collaborating for this purpose with different integrators, providing them with very small form factor instruments, also high performance to meet the requirements of these automated applications, and being able to inspect at very high speeds. Our instruments are also RAG and IP 67, sorry, design. This allows us to place the instruments very close to the probes and minimize in this way the length of the cables. We also have some resources for a proper synchronization with the robots. And this allows for different configurations in single and twin robot systems for doing through transmission ultrasound, phase array, or TFM or related methods. For the spectrum of composites, we cover the different range of applications going from the conventional UT, phase array UT, which normally are used for the low attenuation materials, monolithic laminates, for instance, and also the through transmission ultrasound being able to inspect the very attenuating materials, demanding a high dynamic range. Complex shapes. Okay, this is a very common application in aerospace. One of the most typical ones is the radii inspection. In the inspection of radii, we find different, let's say, deviations or variations from the design in radius, in angle, in concentricity, or position. So we have specific solutions for the inspection of this type of components. Other benefit of our technologies is the possibility to improve the near surface resolution. Additive manufacturing is a typical application and a growing, I would say, application for us. In this case, we need to detect very small things, and porosity is a very common issue that can appear in this type of materials, and normally this type of porosity becomes in very small indications. About the technologies we use in aerospace, and this is our vision of how the technologies have evolved. So today we can do high-speed real-time imaging based on the FMC TFM method, thanks to the last generation GPUs and high-speed 10 gigabit Ethernet data links. So we can cover from the conventional UT method to the most advanced TFM FMC methods. In conventional UT and phase array UT, everything is about getting the best possible beamforming through mechanical or electronic means in the case of phase array UT, and with TFM and PWI and other methods, the goal is to get the best possible image with all the data available in the fastest way. In TFM, we shot element by element, and we capture all the signals that we get in the different elements. So in this way, we can produce a high resolution image. In the case of PWI, we can get this imaging much faster, as instead of triggering element by element, we can generate flat plane waves in different directions and still do a TFM image. So we can get image qualities up to the level of TFM in a much faster way. Even we can get a higher speed than the one we can get in phase array UT. From Tpac, we provide different hardware technologies for conventional UT and phase array UT. About software, we provide different possibilities. We have an open platform in terms of integration. So we build our own software applications on top of this platform both standard solutions and also custom solutions for our customers. So other customers integrate our systems based on this open platform at different, let's say, abstraction levels. We also provide an open data format, and we are compatible with SIB analysis and ULTIS. About the adaptive methods, this is an evolution of the TFM image. So we can use the same FMC data set to learn the shape or the position of the surface and do a TFM image based on this profile. So in this case, we don't need any iteration. So there is no physical overhead, as we found in the phase array UT adaptive methods. We can still get the benefit of TFM doing total focusing in the whole volume. Most importantly, we don't flatten or modify the profile of in the BScan. So we preserve the geometry of the surface. Here is an example of doing ATFM on this webby block. In this video, we can see how the variations of the surface are compensated, so we can still detect the side drill holes using this flexible wedge. In this slide, we can see how we preserve the surface measured by ATFM and detect the different holes compared to a conventional TFM image. One of the applications of ATFM is just positioning or get a better positioning of the part when the accuracy or the tolerance of the mechanical system is not, let's say, perfect. So we can compensate these small or slight variations of the probe position respecting the part, even for flat surface. This is an example using ATFM inspecting the impact damage created in a monolithic composite. Arbitrary wave generation, this is other technology, quite interesting. In normal ultrasound, normally we excite the probe with a negative square pulse. So we can speak in this case about a match acoustics. In arbitrary wave generation, we can excite the probe using different waves shapes, like Gaussian shapes or chirp or burst. And on top of this, we can receive the signals using a match filter. And this match filter, it's like a demodulation of the emitted signal. So in this case, we can talk about match acoustics. The main benefit of this technology is that we can improve signal to noise ratio and the penetration capability of ultrasound. This is how we program different types of arbitrary waves, going from the standard ones like negative, positive, bipolar pulse, to burst pulses, Gaussian, chirp, or whatever wave shape matches better the probe and the on material. This is an example on a real part. This is a very small crack using a normal TFM compared to TFM plus AWG, and we can see a significant improvement of the signal to noise ratio and resolution. This is other example showing an improved of the signal-to-noise ratio using a cheap AWG. Again, other example showing how we can improve penetration and signal-to-noise ratio. And this is the hardware we use, or it's supported this technology. This is the high-end instruments from Tpac. We will see them later with more detail. And this is just an example of an aerospace application using AWG, doing through transmission, and not only getting benefit from the high dynamic range and broad bandwidth that can allow for different applications, including air duty, but also using AWG to improve the sensitivity or signal-to-noise ratio. Other interesting technology and emerging technology last year is called phase coherence imaging, or PCI. In PCI, we look at the phase coherence, and for instance, in this reference block, if we go to, let's say, a clean area, and we measure, there are different ways to measure it, but if we measure the phase coherence, we see that there is a low phase coherence. If we go to a drill, in this case, or a defect, we find that, out that the phase coherence increases. We detect here a high phase coherence. So if we use this phase coherence information in our benefit, we can even get better resolution and signal-to-noise ratio as if we compare it with the standard TFM. This is an example for detection of a crack in a titanium nickel alloy. Here we can see how the resolution and near surface resolution is improved drastically. And this is another example showing how we can increase the signal-to-noise ratio, in this case more than 20 dBs. So about our portfolio for aerospace applications, we have different instruments. All of them are rack design. We have the best performance to size ratio in the market. Data links are 1 gigabit Ethernet and 10 gigabit Ethernet, depending on the instrument. And we also have different IOs and synchronization resources for integration in robotic systems. The smallest member in the family is called Pilot Micro. It's a very small conventional UT system. It has 8 channels working in parallel and 400 volts pulsar. The bigger version is called Pilot. It's the highest end conventional UT in the market. It has 8 channels, again working in parallel, a broad bandwidth going from 50 kilohertz to 20 megahertz. This broad bandwidth allows for a wide range of applications, including air-coupled UT. This module provides a very high dynamic range. We can acquire the data with a 27-bit resolution, which means 156 dBs of information acquired. We can obtain up to 130 dBs of free noise dynamic range. And all this makes it necessary the use of gain control, so we can acquire the signals without worrying anymore about the gain setting. We also have 400 volts unipolar and bipolar pulsar, and we have as an option, we can also include AWG pulsar. Going to the phase array instruments, Explorer is a high performance instrument. We have multiplex and full parallel configurations. The maximum one is 128, 256 channels. And we can also provide up to 8 conventional UT channels. For this Explorer, we can provide also a battery kit with a rack design, long duration battery with a quick replacement and a charge level indicator. Explorer Max is a higher performance module compared to Explorer, thanks to the 10 gigabit Ethernet link. And its configuration is a full parallel one with 64 channels. And we also have the possibility to add AWG pulsar. This is the 128 channels version of Explorer Max. In this case, we have two 10 gigabit Ethernet links. This is Pioneer. This is the most complete and advanced ultrasound system. We can combine phased array UT, PWI, TFM, PCI, and also conventional UT. We can also include AWG pulsar, and we have different configurations, multiplex and full parallel, up to 1024 and 4096 channels. In this case, we can have up to 4 10 gigabit Ethernet links. Finally, Voyager is a portable platform for MRO, for maintenance of aircraft. This is an all-in-one rack wheel case solution, integrating everything, including the CPU with a 12-inch screen, keyboard and touchpad, and the Tpac Explorer. And there is a slot also for the UT probe and a long duration battery. And that's all. Thank you very much for your attention.
Thank you, Fernando, for your fascinating run through there of some of the products and services that Tpac offers. I've got just a few questions there from. Actually, before we go into the questions, I should point out that also on the right-hand side of the screen, very handily, if you haven't noticed already, is a brochure for Tpac's products. Just in a kind of summary format. In case you want to download that, you can do that from the right-hand side of the screen. Okay, so we just got time for a few questions here, Fernando. I just wondered, do you have any advice or tips for engineers that want to optimize testing in any way? Is there anything that you would say? I know it's quite a general question, but is there any sort of common advice that you would give?
Yeah, we normally it's very common for us to start from an NDT problem. So in these cases, it's very useful to have a number of different technologies to test in the lab. So we have in this case different solutions oriented to labs. So we can provide this type of services, in fact, for the start of a new project or solving a new project or new problem, or improving an existing one. So in this case, I would recommend either to have a system with all these capabilities in-house, or contacting us to study this problem. We have different. We have people specialized in NDT, in physics also. So and some resources to immersion tanks to do this test. So we can test many times with different parts provided by the customers. Yeah, I would say that this is the best way to improve or solve a new NDT problem.
Okay, great, thank you. And related to that, I just have a question here about selecting equipment and making decisions on things like frequency range and probe type and resolution. I mean, have you got any advice on when you're approaching an NDT task? I mean, how would you advise going about that? Again, to get best advice from your supplier, or?
Exactly. We don't manufacture probes, but we design and specify them many times. Again, we have people expert in probes design and the physics behind. We can simulate the acoustic behavior of these probes. Yeah, we can recommend our customers a design, even some suppliers, or we can provide them, supply them as a part of the scope in some project.
It sounds to me like you have a very close relationship with your customers. Is that right? Is that true?
Right. Yeah. Of course, we have a wide portfolio and products, and this is let's say our core technology and the core of our business. But normally our business starts with an NDT problem. Not always, of course, but our approach to the market is not only providing good technologies, but especially providing a good support from the very beginning. Also during the stage of integration, either with the NDT integration or the software integration. So this is our approach, and not just selling one of our products. Like of course, it's part of our activity.
Yeah. Okay. I understand what you mean. Okay. Wonderful. Just one final question here. Just quickly. I'm sorry if anyone's got any questions that they would like to ask. Then do contact Fernando afterwards. I guess that email address will come through to you, will it, Fernando? Eventually, it will come to you. Contact at Tpac. Yeah.
Yeah.
Yeah. Okay. Wonderful.
Yeah. It's yes.
So this last question is just on calibration. I mean, is that something that you also advise on? I mean, how can an engineer improve calibration? I mean, how often should it be? That sort of setup and calibration technique.
Sorry, I didn't catch your question.
To do with calibration, Fernando, should that be something that's done? I mean, do you have any advice on calibration? Should it be done? How regularly? How often?
Oh, okay. This depends on the customer or regulation or that our customers use. But we can provide, of course, this type of services to calibrate the instruments. But this depends on the industry. Normally, in aerospace, every year they should be calibrated.
Yeah. Okay. Good stuff. All right. So we'll end the webinar there. Thank you very much, everybody, for your attention. Fernando, thank you for your presentation and answering those questions. Is there anything that you would like to add or end on?
No, it's okay. I would be happy to hear from you from any NDT problem you could have. We will be more than happy to help.
Great. There you have it. Come to Fernando with your NDT problems. He'd like to help you. So brilliant. Okay. All right. Well, again, just thank you. This webinar will be available to view afterwards. So as well, if you want to go back over anything that Fernando's discussed today. But all that's left for me to do is just say thanks again and have a great day.
Thank you.
Thank you.